And then as soon as it starts, I can close this monitoring tab. All right. Okay, I can close that one. Pop this one back in. And I got well, I thought I had a Chrome window open for the test. Maybe I have closed it already. That's okay, I can just open it again. That would be the same test that I distributed to you guys on Monday. So let me go back to Monday's channel to retrieve that file. Alright, there we go. Alright, so today's plan is to go over the practice exam, which is the actual exam from last semester. And then if we do have time left, we can go ahead and continue with the discussion of big O, big omega, and big theta. So it kind of depends on how much time we spend on the exam. The first 5 questions should be pretty quick. The last 4 may take a little bit longer because those involve the use of Boolean algebra. So that might take a little bit longer. We'll see. Alright, we got about 30 seconds. And I am going to turn to question number 1. And probably zoom in a little bit. There we go. And for those of you who have been tracking, what kind of audio setting I have been using, I have changed my headset already because my son's other headset has died, so he took mine, and then I took one of his that I fixed a long time ago. Not sure whether you guys can see it or not. Well, the time has started, but basically the cat chewed the cord of the headphone or the headset, and I fixed it. I'm pretty good with the soldering station, but the problem is, when you fix it with solder, it's just gonna break there, because there's no strain release. So I did something like this. Hot glue, yes, that is hot glue. Just a big blob of hot glue to to give it structural integrity. Looks really ugly, but it works. So I'm not gonna throw away a good pair of headsets unless it really dies. So there's that. Okay. All right. So let's go ahead and get started with the questions. So question number 1 is in the format of giving you a particular R defined over a particular X, and we want to describe the relation R in the following terms. So each one needs to be either true or false. You cannot leave it blank. If you leave it blank, there won't be any points for that. Point out why it is false. Okay, if it is false, you have to give me an example of what makes this particular attribute false. If the answer is true, then you don't have to do anything. But if it's false, you have to give me specific values to put into the definition of that particular property, and then you tell me why it is false. Or, in the case of partial order or total order, you can just refer to the earlier terms and say it is not partial order because it is not one of these earlier ones. All right, so are there any questions about the format of the question before we actually get to the answer to this particular question? Okay, looks like there are no specific questions. All right. So what I'm going to do is I will, I suppose I can copy everything here to Joplin. So I am putting this into Joplin here, and let's see how that turns out. So it turns out okay, and I'm gonna put here, and this is for practice exam 2, and then we'll look at each one of these properties and find out whether it is true or not. All right, so let's start with whether something is reflexive or not. So what is the definition of the property of being reflexive? So that's what you need to start with. Okay, you have to remember the definitions of all of these properties, because that's where we go. Okay, because an explanation of that is just kind of a verbal explanation is not going to be as concise or nor as accurate as the original mathematical definition. So does anyone remember what is the definition of a relation R being reflexive? And I'm going to start typing here. So we know there's a for all, right? And for all elements in X, so I'm going to say for all E in X. So I'm going to close the equation first, just so that you can see it on the right hand side of the, for all E in X, there's a tuple EE that is in R. So Jonathan is correct. Okay, so I'm going to finish the actual definition first. All right, so now what do we do? In other words, in this case, it is not the case, right? It is not reflexive. Why is it not reflexive? Because X has 3 elements. Other than the element 2, the element 0 and the element 1, they do not have a 0, 0 nor a 1, 1 in the relation that we are looking at here. So the correct answer in this case is you first answer with false, and then you specify the elements in R, in X that is making this particular R not reflexive. Okay, not reflexive because 0, 0 and 1, 1 are needed to make R reflexive in this case. Now 2, 2 is needed too, but 2, 2 is already in R, so we just have to mention the ones that are missing at this point. Are there any questions about why this particular relation R is not reflexive? I'm just taking a look at the text channel here. Okay, no questions, or yes? Okay,
I have a question.
Yeah, go ahead.
Could you just quickly write down uh, the representation of the relationship that would be correct?
Well, that is a good question. So does anyone want to answer the question? What would make R reflexive? In other words, the first thing we need to do is to look at this particular quantified statement or quantified expression, Boolean expression, and we ask the question, what would make this quantified expression true? So instead of me just giving you the answer, I want you guys to look to
Will,
understand the definition first. Go ahead.
will we have to include 2, 2 into like a tuple 2, 2?
The tuple 2, 2 is already in there to begin with, so but that's not sufficient. What else do we need? I mean, I already wrote it in the answer. All right, so let's take a closer look. Okay, so instead of using X here, I am going to make it even more clear by listing the elements in the set X. So for every element in the set of 0, 1, and 2, EE, has to be in R. So what do you think needs to be in R in order for R as a relation to be reflexive? Okay, so E is going to bind to 0, E is going to bind to 1, and E is going to bind to 2. And for every single value of E, okay, we need EE to be in R. So what elements do we need to be in R? That is correct. Adam is correct. 0, 0, 1, 1, and 2, 2, they all have to be in R in order for R to be reflexive. We need all three in order to be. We need all three to be elements in R in order for R to be reflexive. When I said 3, I meant 0, 0 as a 2 tuple, 1, 1 as a 2 tuple, and 2, 2 as a 2 tuple. There we go. All right. Okay. Well, you can also look for the opposite, because if it is not reflexive, that means this expression is not true. And if this expression is not true, then Jonathan is correct. It simply means there exists an E in the set such that EE is not in R. Then you just have to tell me at least one of those EE that is not in R, and that would be the reason why this R is not reflexive. So that would be another way to look at this. But either way, we start with the definition. So now we are moving on to symmetric, unless there are additional questions about reflexive. So with symmetric, what is the definition for a R to be reflexive? So let's go ahead and take a look at the definition of being symmetric. So now we say we have to pick two things. Well, I shouldn't say pick two things. We have two variables that are both universally quantified. So now we have EF, and we say both of those are in the X that we are interested in. I'm going to close this right away so that this way you guys can focus on the right hand side. So what do we want in the parentheses this time in order for us to say that this relation R defined over X is symmetric? This one is a little bit more interesting. Okay, the other one is just saying, okay, we need these things to be in R in order for R to be reflexive. That's actually not very exciting. This one is a little bit more exciting. This one says EF is in R if and only if, okay, so if and only if is a left-right arrow, FE is also in R. Alright, so that is the definition of how a relation R defined over X is symmetric. We need this quantified statement to be true. So in this case, is it true or not? All right, so I'm looking at the text channel. If E and F are in X, then FE and EF must both be present or not in R. Okay, that is true for every way to choose E and F. Okay, that's to add to what Jonathan had already typed. It is for every way to choose E and R in X, FE and EF must be both in R or both not to be in R. Alright, and then Aman's description is opposite two tuples should be in R for elements E and F, otherwise no two tuples involve F and E. That's a little bit vague. So in this case, is it true or not? Okay, so that so now we're trying to go after the actual answer. Is it true or not? Yep, it is symmetric. Okay, so in the case that it really is symmetric, there's no further explanation needed, because we only want to have counterexamples given when it is not the case, when it's not a particular property. Alright, so now we're dealing with anti-symmetric, which is even more interesting, because this one does not have if and only if. It only has if. Okay, it has implication. It only goes in one direction. Alright, so I'm catching up on the text channel here, On the text channel, it says 2, 2 is in it, and 2, 2 is in it too. In other words, if I choose E to be 2 and I choose F to be 2, then we have this statement being true because E is 2, F is 2, right? 2, 2 is in R. Yes, that is the case. That's how R is defined. But what about FE? Well, because F and E are really the same, so if EF is in R, then FE, if EF is in R, then FE has to be in R too. So now we have both sides being true, and that takes care of the case when E and F are both 2's, okay? That's not a problem. What if E is 1 and F is 2? Well, then they're both missing, right? Because 1, 2 is not in R, but 2, 1 is not in R either. So with if and only if, as long as the two sides, the left-hand side and the right-hand side of the if and only if they're both true, the if and only if is true. If they're both false, then the if and only if is also true. So we are good here. So it goes all the way back, okay? This goes all the way back to what is if and only if, okay? The truth table of if and only if comes in handy in this case, in case people have forgotten that truth table. So with antisymmetric, it is a little bit interesting because it says for all E, F in X, which is the relation, what the relation is defined over, we basically say EF in R. Okay, I'm going to use the shorthand here because this is taking a little bit longer to type, and I'll just type, I'll choose a different notation so it's easier to type. ERF is basically the same thing as EF is in R. And then we have a conjunction, which is a wedge, FRE, and that implies, okay, we have a right arrow in this case, it implies E and F are the same. And let me put in some extra parentheses just so that there's no way to misinterpret the nesting of the expressions. Alright, so this is the definition of antisymmetric, and I think I'm missing one close parenthesis. There we go. So in this case, we basically want to say for every way to choose a value for E and then for every way to choose a value of F, we want to make sure that ERF and FRE, so when FE is in R and EF, okay, let me take that back. When EF is in R and when EF is in R and FE is in R, we want E and F to be the same. In this case, it is true. So this one is true too. So there's no further explanation needed. Oh, am I missing a backslash in? Oh, right. Yes, I'm missing the one back here. Thank you. There we go. All right. So this one is rather easy. Let's look at transitive. Transitive looks a little bit complicated when we look at the definition, but the concept is not really that much more complicated. But this time we need three universally quantified variables. So we have E, F, and G in X. And in order for a relation R that is defined over X to be transitive, we want the following to be true. So we want this thing here to imply this thing over here, and the thing on the right hand side of the implication is ERG, and then the thing on the left hand side is ERF and FRG. There we go. So now we look at this particular universally quantified expression, and we ask, is that true for this specific X and for this specific R? The answer is true, okay, because we are looking at the conjunction here, and we ask, can we make this conjunction true? The answer is, yeah, we can make it true if we choose E, F, and G to be all 2's, right? Because the only relation defined here is 2, 2, but that means 2R2 is also there, so it really is transitive. Yep. We want E, F, and G all being 2. anti-climatic. That is not a property of a relation. Not in a mathematical sense. Maybe for people. For people relations. That would be a difficult class to teach. Good thing I'm sticking with just math and computer science. So it is transitive, yes. Okay, so let's put it through here. All right, let's talk about comparable. Is R comparable in this case? Well, it definitely is not. Okay, but then we want to explain why it is not. Some people is going to say, well, anything that's comparable is also going to be reflexive. Since it's not reflexive, it is not comparable. That would not be a good answer because it is not giving me an example. Now you can reuse the example of not being reflexive, but you cannot just say that because it is not reflexive, it is not comparable, because that's not what the question is asking. The logic makes sense, but it is not what the question is asking. But before we go there, I think it's important to understand what makes a particular relation comparable. Okay, so this one is actually pretty easy. Okay, we basically say for all ways to choose a value for E and F, and they both have to be a value in X. We want the following to be true, and this one is something or, which is a V something, and we basically want to say, doesn't matter how you choose E and doesn't matter how you choose F, we want ERF or FRE. So in this case, this set definitely is not meeting this requirement because you can give one of the many examples, because you just need one in order for the entire universally quantified expression to be false. So you can basically say, false because when E equals to, there's so many examples you can choose, right? So when E equals to 0 and F equals to 0, 0, 0 is not in R. Okay, that's just one of the many examples you can choose. All right, so I am going through the text channel. Don't read this tag, including that one, right? So problem has to take less than average 10 seconds per population 100 to be anticlimactic. Okay, I see. Okay. So no questions for me. All right, I'm gonna move on then. So the next one is partially ordered. So now you have to remember what makes a particular relation partially ordered. So this one, you don't have to give me examples anymore. Even if it is false, you don't have to give me examples. So in this case, you can say it is false because R is not reflexive. Because in order for a relation to be partially ordered, it has to be 1, reflexive, 2, antisymmetric, and 3, transitive. This one is not reflexive. Totally ordered is even easier to answer. Okay, because in order for something to be totally ordered, it has to be partially ordered. So this one is false because R is not even partially ordered. Partially ordered. There we go. All right, so you guys are getting it in the text channel. Looks like everybody is getting the answer to this particular question. So let's move on to the next one. All right, so question number 2 has a slightly different format. For this one, I give you X, and I want you to give me the relation defined over X such that R has the following property. It is partially ordered, it is not comparable, and it is not symmetric. All right, so let's go ahead and just copy enough of this question here. Now, the other part of the question, you probably want to read ahead of time, just to understand that it is possible. Because if there is no way to make such a R or relation, you have to explain using the quantified expressions to tell me why it is not possible to have a specific combination of the attributes. So there has to be a conflict somewhere. If such a R does not exist, your answer should show your understanding of the relation properties and the reasoning based on these properties. So let's check out this one and see whether it is even possible or not. If it is possible, we just have to show an example. If it is not possible, then we go ahead and explain why it is not possible. Alright, so we want it to be partially ordered. Okay, so in order for something to be partially ordered, we know it has to be reflexive, right? So right away we can say, okay, I'm not going to use a math notation anymore, because in this case I just need to show you a set. I don't need to use mathematical equations like over here, so I'm just going to use regular text here. So we know 0 0 has to be here, 1 1 has to be here, and then 2 2 also has to be here. Next, what else do we need in order for a relation to be partially ordered? So we need reflexive, we need antisymmetric. Antisymmetric is easy, okay? If I don't do a single thing, it is automatically antisymmetric. Oh, my watch just buzzed me, so it's time to take roll. Yes, I am taking roll today. And let's see, today's row taking activity is down here, and now it should be visible to you. And then the row taking word is simple, it is just exam 2. Yeah, I know, very anticlimactic, as you guys said. So exam 2 is the word for row taking today. I should have used the word anticlimactic if I just knew that you guys would use that word. But in hindsight, it's always 50-50. 20-20, sorry, not 50-50. 50-52, actually, kind of. Depends on how you look at it. You want to be a mantis shrimp. Mantis shrimps are not only do they have super duper high resolution vision, they also can see in a much wider spectrum than we can. And they can also stun their prey by using their claws here, by using a shock wave underwater. They can crack aquariums using the shock wave. Very interesting organisms. Totally unrelated to this class though. Alright, so getting back to this question. Alright, so antisymmetric is kind of automatic by itself. So what else do we need? We also need it to be transitive. And guess what? I don't have to do a single thing for this to be transitive, okay? Because it is automatically transitive. We don't want it to be comparable, because if it were comparable, it would have been totally ordered, right? So we don't want it to be comparable, and that's easy to do. I don't have to do a single thing to make something not comparable, because to be comparable means I have to add things usually to make it comparable. I don't have to do that. But the last one is tricky. I don't want it to be symmetric, and it is symmetric at this point. Alright, so Jonathan said, yep, that's a good summary of what we want, but we don't want it to be symmetric, and it is symmetric at this point. So now we have to make it not symmetric without breaking any of the other things that we have earlier. Okay, so what are we going to do? Well, there are a few things we can do here to make it not symmetric. How about we just add 1, 2 to the whole thing? So let's rethink about all of those properties. First one is it still reflexive? Yeah, reflexive is easy, right? For a particular relation to be reflexive, we just need to make sure that in this case 0 0 1 1 2 2 is a subset of R, okay? And as long as we have those three, we're good with being reflexive. That's good. The second one is antisymmetric. It is still antisymmetric because 2, 1 is not here, so I don't have to worry about this thing being not antisymmetric. All right, cool. Is it transitive? It is still transitive because adding 1, 2 to this whole thing doesn't cause any problem to make it not transitive, because you can choose 1, 1 and then 1, 2, so that 1, 2 is there. So it is still transitive. And let's take a look at comparable. It is still not comparable because that is not what we want. And now it is also not symmetric because 2, 1 is missing and it is not symmetric at this point. Alright, so in the text channel, there's a request to explain antisymmetric again. I know some of you is going to hate this because I'm just going to point back to the expression, because that really defines what antisymmetric means. At this point, there's no way I can choose E and F so that this expression is false. So no matter how I choose E and no matter how I choose F, as long as E is an element of X and F is an element of X, this expression here, this entire implication, is still true, so it is still antisymmetric. Yes, I am definitely like a pointer. It's more like a reference. I can move the information around and then do garbage collection, as they say. But it really is important to go back to be able to read the definition as a mathematical expression and then use that to answer the question. Okay, so then Jonathan Camarena is asking, is this definition the same for antisymmetric? For all EF in X, R, ERF, if and only if that is not antisymmetric, that is symmetry. That is symmetry, which is just one line before that. Antisymmetric is this specific one. So the question is, can you find me a case where E is an element of X, F is an element of X, in other words, E is 0, 1, or 2, and then F is also 0, 1, or 2, such that this implication is false? So in order for this implication to be false, what do you need? You need the left-hand side of the implication to be true, because if the left-hand side of an implication is false, then the implication is automatically true, so there's nothing to worry about in that case. So the only way, yeah, that was a warning from my for a meeting starting at 6 o'clock, but back to this thing here. So in order for this implication, I'm pointing to the implication operator here, in order for the implication to be false, I first have to make the left-hand side true, which is impossible in this case. Well, actually, I take it back. It is possible because we can choose E and F to be the same thing. Okay, so E and F can both be 0, they can both be 1, they can both be 2. But if they're both 0, 0, 1, 1, or 2, 2, then we can also say E and F are the same. So now you have to look at the other case, which is, what if E and F are different? Then it is not possible because the relation is not symmetric. So let me look at the text channel here. Is the reason why R is transitive is because we cannot make it false. Okay, that's one thing you can also say is we cannot make it false. And if you cannot make it false, then it's automatically true. But let me take a look at the example here. So if you choose E to be 1, F to be 2, and then G also to be 2, then it is transitive. If you choose E to be 1, F to be 1, and then G to be 2, it is also transitive. That is correct. You can also choose E, F, G all being 0. You can choose E, F, G all being 1. You can choose E, F, G all being 2, and it is still transitive. So the bottom line is, I cannot make this expression false. And once again, the key to make an implication false is to make the left-hand side true first. And in this case, in order to we cannot there's no case where we can make the left-hand side true but the right-hand side false. That is basically the idea. Yeah, it is an implication. So implication is a very important concept because the truth table for implication basically says the only time you can make an implication false is when the left hand side is true and then the right hand side is false. That is the only time. Alrighty. So now I think we got the answer. This is one of the many possible answers, because if you just want to make it not symmetric, you can also introduce 2 1 into it without the 1 2. You substitute the 1 2 with the 2 1. That would also be a correct answer. Or you can use 0 2 2 0. That would also make it not symmetric. But you can only use one of those. Now, if I just add one more thing here, now we are in trouble, because now it is also not transitive. All right, so can you guys see how YR is now also not transitive, which is not what we want? Okay, very good. The reason why it is not transitive at this point is because if I choose E to be 0, F to be 1, and then G to be 2, then the expression that we need inside the quantifier of being transitive, this expression here is now false, because 0, 2 as a 2 tuple is not in R. That is why. 0 should have been 2. Not really. Now, if you put a 2 here, then it is no longer anti-symmetric. It would still be transitive in this case, but it would not be anti-symmetric, because now we have 1 2 and 2 1 both in the relation R, but 1 and 2 are not the same, and therefore it is no longer anti-symmetric, but it would still be transitive. Because if you choose E to be 1, F to be 2, and then G to be 1, hey, not a problem, because 1 1 is here too. If you choose E to be 2, F to be 1, and then G also to be 2, it is also not a problem, because 2 2 is also here. So there we go. So are we good so far? So let me go back and correct my answer, because I want to make sure that this is the correct answer for what the question is asking. Are there any further questions before we move on to the next one? So comparability requires reflexivity. That is correct, because everything has to relate to everything else, including itself. That is why. Alrighty. So if you look at comparable, okay, there's no rule here saying that E and F have to be different, right? So that means E and F can be the same, and if that is the case, then we need we need an element to relate to itself in order for this OR to be true. Now, obviously, when E and F are the same thing, then the disjunction or the OR is either true or false, because on both sides it's either true or false. It doesn't matter, because we just want the disjunction to be true, so they can both be true at the same time, which means E and F are the same in that case. No, an empty relation is not comparable. It is not. It is transitive, but not comparable. Yep. So I think a lot of the questions stem from they stem from not fully understanding the quantification or the implication operator. So that means when you guys study, you kind of have to go all the way back to make sure that you understand how the quantifiers work, and also how specifically the operator, the and the or, I think you guys got it down already. If and only if is pretty easy to, because it means both sides have to be the same. Okay, they can be true true, they can be false false, but they cannot be one side is true and the other side is false. Implication is the difficult one, because implication is the one where the only time the implication itself is false is when you have true implies false. And that is a little bit unusual compared to the other operators because it is asymmetric itself. All right, so Jonathan C is typing, but I'm gonna continue with the next question. So question number 3 has the same format as question number 1, but this time, the R is a little bit longer. All right, so the new text channel is the new content in the text channel is it helps me to convert X implies Y to not X or Y. That is true. It depends on each individual. Some people like to boil it down to operators that we are already familiar with, which in this case is boiling implication down to a negation and a disjunction. And then Jonathan W says, I just remember there's only one case you can have it false, and it is the left-hand side has to be true, and then the right-hand side has to be false. So either way works. Okay, it all depends on how you want to process this. But you have to choose a way to kind of take that into consideration. All right, so let's take a look at question number 3, and I'm just going to copy this over to Joplin. And there we go. And now we want to evaluate this one, and we ask, is it reflexive? Question mark. And we look at this and go like, yep, it is reflexive. Right? It is reflexive because 0, 0, 1, 1, 2, 2, they form a subset of R, and that's why we're good. And Wade is typing. There we go. Do we have a copy of the practice exam available to us as well? To phrase Darth Vader, I find this question troubling. Not so much your lack of faith, but the question itself, because I posted this question, I attached it in the text channel of Monday. Yes. All right, so second question is, let's see, the second one is whether it is symmetric or not. Okay, symmetry. And let's take a look. I mean, I cannot remember the answer. These are all automatically generated by a program that I wrote. So, I cannot possibly remember the answers to every single variation. So in this case, the answer is no. Okay, it is false. Since the answer is a false, now you have to say, well, since symmetry is defined like this here, so what value of E and what value of F will make this statement here false, and therefore the universally quantified statement itself is going to be false. And Jonathan is right when E equals to 0 and F equals to 2. Because even though we do have 0, 2 here, but 2, 0 is missing. Okay, so that's why, when E equals to 0 and F equals to 2, it explains why this particular R is not symmetric. Very good. Any questions about why this R is not symmetric? Okay. Now, to be more complete, we can say when E equals to 0, F equals to 2, then E, R, F, and if and only if F, R, E is false. Because one is true, the other one is false, the other one is true, and that's why the if and only if is going to be false. Next one is anti-symmetry. Anti-symmetric question mark. All right. So let me take a quick look here, and the answer is it is antisymmetric. Okay, it is true, it is antisymmetric. And since it is true, we don't have to support it using examples, because counter examples are only useful when we want to prove something being false. But if it is true, you cannot use counter examples. All right. Yep. Does anyone want to give me what you think is a counter example? Because if you can think of one counter example, I can show you why it is not a counter example. Yes, that's a double negation right there. It is not a counter example because not is negation and then counter is also negation. Okay, nobody is thinking of a case. I mean, don't be shy, okay? Because the idea here is if you think there's a case to make this expression here false, then it is my job to point out why it is not false. Okay, so if you think you can find a value for E and a value for F to make this expression false, then I will have to explain why that expression is actually true for that specific combination of E and F. Alright, so the hint is target the tuples where the first element is not the same, and then we want to see if there's symmetry over there. Yep. Alright, what about 0 and 1? Okay, so let's take a look at that. Okay, so we'll make it nested. Alright, and gonna scroll here. Okay, so what if E is 0 and F is 1? Alright, so we're gonna look at the actual definition of antisymmetry. So we want the and then the implication. So in this case, we have to. This is what we are evaluating. Okay, we're evaluating 0R1, and I'm going to use the C and here 1R0, and then we have the implication here, and we say 0 equals 1. Okay. All right. So let's focus on this expression. And ask, well, what is the value of this entire expression? The answer is, well, let's evaluate the left-hand side first, right? So we're going to focus on only one side of this, which is the left-hand side of the implication. 0R1 is not here. It is false. Okay, so immediately we have a false here. So false and something else is always what? Yes, that was a question directed to the class. Okay, false and whatever is always false, because false. Okay, very good. So if you have false for the entire conjunction, that means the left-hand side of the implication is false. And I'm not going to sound like a broken record. It suffices to just say that the implication is true because of that. Does that work? So once again, it boils down to the understanding of implication, because that is why the implication is true. Yep. All right. So this tells me, when you guys are studying, you kind of really have to not just look at implication as, oh yeah, I understand what implies means in English. No. That's you can forget about the colloquial understanding of implication here. You have to get down to the actual definition of implication. X implies Y is the negation of X or Y. You have to get to that one, or use the truth table. Either way is a good way to understand what implication is. But in this case, the entire implication. Okay, let me put an extra pair of parentheses here. The entire implication is true, so it is not a counterexample. Yep, you can easily pop out a window from Discord. You can probably just look on the internet. Just Google for Discord pop out. Oh, between Joplin and Stream. I'm guessing that's your own Joplin, Wade. Yep. Having a second monitor definitely helps. I will tell you that. Having a 4K monitor helps even better. Helps even more. All right. Yeah, I'm not sure that's going to be helpful unless you're wearing one of those. I will show you guys how you can make a 4K resolution on the laptop being helpful. Just give me a second here. I'm going to get my prop. Well, it's not a prop. I actually use this thing, just not in when I'm teaching. Okay, I cannot wear this when I have a headphone. When I have this kind of headphone, if I have my usual earplug, I can do it. But this is what you need. Okay, you need a loop of some kind to actually see the details when you have your 4K packed onto a 13 or 14-inch monitor. Yeah, that's not gonna. Yeah, you need tools. I mean, I know my eyes are not as good as yours, but I cannot think of anyone with their eyes good enough to actually make use of a 4K resolution on a 13-inch monitor, except for a mantis shrimp. Yeah, so you need to be a mantis shrimp to do it. I think octopi also have high resolution eyes compared to ours. There you go. Okay. I can barely do it. I can barely use 1080p, which is what I have right now on a 13-inch laptop. Just barely. Alright, so next we are moving on to transitive. Okay, is this transitive or not? Okay, so let's take a look. 1002 12 is not here, so it is not transitive. False. There we go. Okay, so to know whether something is transitive or not, because it's also based on implication. Okay, so let's go back to the definition of being transitive. It's right here. So because it is still based on an implication, so the first thing you need to do is to find a way so that the left-hand side is true. And you want to find a non-trivial case, because if you say, oh, when E, F, and G are all the same, then the left-hand side is true, that is a trivial case, because that automatically makes the right-hand side true too, which means it is useless to you. So you need to find a non-trivial case where E, F, and G at least they cannot all be the same. Okay, I'll just put it that way. They cannot all be the same. So if you can find a case where E, F, and G are not all the same, and this conjunction is true, then you have a chance to make transitive false. So let's go back to our current example. Now this is false because if I make E equals to 1, F equals to 0, and then G equals to 2, then it is not transitive. Because in this case, 1 R 2 is not in R. It's false. Okay, that's really redundant. I should say 1 R2 is false. 1 does not relate to 2. Does that work? Does everybody understand why this particular relation is not transitive? Because ER1, 1 R0 is true, and then we have 0 R2 is also true, but 1 R2 is not true. That is why. Yeah, transitive can be a tricky one. Can be tricky. Next one is comparable. Comparable. So with comparable, this one is already reflexive, which means you cannot give me the same example as what makes it not reflexive, because we know it is reflexive. So now you really kind of have to look at 0 and make sure that 0 relates to all of the values. Okay, so 0, 1, and 2. So we know 0 relates to 0 here, we know 0 relates to 2 here, and we also know that 1 relates to 0. So 0 passes all the tests. Now we check 1. 1 relates to 0, 1 relates to itself, 1 also relates to 2. So, well, okay, the other way around, but we just need 1 or the other way because it's an OR. So 1 is not gonna make it not comparable. So now we move on to 2, so we can see how 2 relates to 0, or 0 relates to 2, because it only needs to be one or the other. And we can see that 2 relates to 1, 2 also relates to itself. So this one is actually indeed true, it is comparable. Are we good so far? Does everybody understand why this particular R is comparable? So now we are moving on to the easy ones, because partially ordered is easy, because it's lacking one of the 3 necessary properties to be partially ordered. We'll say it is false because R is not transitive. Okay, and is it totally ordered? That's even easier. It is also false because R is not even partially ordered. There we go. So that's the full answer to this specific question. Jonathan W is typing, so I'm gonna wait until he's done. There we go. So which notes had the requirement for totally ordered? It is still in the relation module. You need it to be partially ordered, and then on top of that you need it to be comparable. So even though in this case it is comparable, but since it's not partially ordered, it cannot be totally ordered. So you need a relation to be partially ordered and on top of that comparable in order for the relation to be totally ordered. There you go. Well, the good news is exam 2 is open book and open notes. You guys can use Google even if you want to search for the definition of these terms. So the definition, or having the definitions available to you, is not the problem, but having a thorough understanding of the concept and being able to apply that during the exam, that may be the challenging part. So that means, just having these definitions, at your fingertips is only part of what you need to succeed in the exam. The other part is actually being able to apply the definitions during the exam. So there you go. All right. And then Jonathan typed, so partially ordered and totally ordered are the easiest ones to do time-wise, assuming that the earlier ones are done correctly. Yes, because if you have the earlier ones and you're done incorrectly, then those two would also be wrong, and that's gonna hurt. Can we create a program to output whether AR is reflexive, symmetric, and etc.? Of course you can. I mean, anything that already has a mathematical equation to define it can also be, you can use a program to do all this evaluation, right? I mean, there's no, yeah. I'll just put it that way. If I can use a program to automatically generate the questions, what do you think the answer to that question is, right? I mean, you guys don't expect me to actually, manually evaluate each case to come up with the right answers, right? All right, so here's question number 4. And once again, we want to evaluate. Wait, is that what we just did? Yep, that's what we just did. So now we're moving on to question number 5. So question number 5. Now, obviously, if you're thinking, can we use a program to evaluate all of this stuff here? The answer is yes. The question is, are you sure your program is working correctly? Because if your program is not working correctly, it's going to get, a lot of things wrong, and you won't even know about it. So that presents a new level of challenge, even though it seems to be a way to quickly answer the questions. Alright, so given that x is 0, 1, and 2, can you come up with an example of a relation R defined over x such that R is, we want it to be reflexive, we don't want it to be anti-symmetric, we don't want it to be transitive, we don't want it to be comparable, but we also want it to be symmetric. Okay, so let's go for this. Okay, I'm just going to copy this portion because x is the same for all of the questions, so that's not going to be too big of a problem. All right, there we go. So I'm just copying and pasting the properties here. So now we want to define R to satisfy all of those things. Reflexive, once again, is the easy one. Okay, we just need 0, 1, 1, 2, 2 to be in the set. Now it is reflexive. Alright, so now the rest is to say, is it symmetric right now? The answer is yes, it is definitely symmetric right now. But we want it to be not anti-symmetric. So in order for this to be not anti-symmetric, we need to have a pair of tuples where they are mirrors of each other, okay? Because without that, it is automatically anti-symmetric. So we'll just pick, let's pick 0 and 1, okay? But we need both of them to be here in order for this to be not anti-symmetric. So right now, it is not anti-symmetric. But it is definitely transitive at this point. So we want it to be not transitive. So we'll have to add something here to make it not anti-symmetric, but we also want it to be symmetric at the same time. Oh, excuse me, transitive. So right now it is not transitive. It is transitive. I correct myself. It is transitive right now, but we don't want it to be transitive. So the question is, can we add something here to make it not transitive without breaking the other ones? Can we remove 0, 0? Well, if you remove 0, 0, it is no longer reflexive. So it breaks one of the required properties if you remove 0, 0. Alright, so Adam says add 1, 2, and 2, 1. If you add 1, 2, and 2, 1, that will make it not transitive. It will still be symmetric, and it is not comparable. Or is it? Nope, you cannot just add 1, 2. Because if you add 1, 2, it will not be symmetric anymore. Because in order for the relation to be symmetric, if 1, 2 is there, you better make sure 2, 1 is there too. So if you add 1, 2, then 2, 1, has to be there. Yep. Alright, so we might have a case where it is not possible. Okay, so if we add 2, 1, and 2, 1, 1, 2, and 2, 1, then it is no longer transitive, but it is still symmetric. So now the question is, if you think it is not possible to have all of these at the same time, the question is, how do you argue? How do you reason it out and go like, nope, it is not possible? Instead of using the argument of, I spent 15 minutes on this question and I couldn't find a case, that is not a proof. That is not actually explaining why it is not possible. That is just a statement saying that I cannot find a case like this as described in 15 minutes. So how do we prove this one? Nope, induction is not going to be helpful here because this is a fixed case. We have a fixed number of elements, so it's not going to be brute force. Okay, that's That means you have to look at that means you have to look at every single way to have a subset of x Cartesian product with x and show every single one of them to not have all of these properties that we want. And you have to present every single one in your answer in order for that to count. That may not be a very good way to do it. So we are looking for two or more properties where they are true at the same time. We end up with a contradiction. So proof by contradiction is the idea, even though I don't need this to be a formal and official proof by contradiction. But you guys got the right idea, okay? So where's the conflict? The conflict is about symmetry and not anti-symmetric is not a problem. Okay, that's not a problem. Yeah, Google. Nope. I think most of the time I specifically make sure that my questions cannot be answered easily by Googling. Or better yet, when you Google, you find the wrong answers. So how do we reason this out? Reflexive is not a problem, okay? It doesn't really interfere with anything else. So what is being interfered? When we add 1, 2, and 2, 1, it is remaining to be symmetric, which is good. It is remaining not to be anti-symmetric, that is good too. But the problem is, it is, wait, hold on. Okay, so what is the conflict here? I'm confusing myself. It happens sometimes. I think this is the answer, right? Okay, let me double check. So we got 1 relating to 0, 1 relating to 2, and then this is the answer. It is not transitive. This is not transitive right now. Okay, let me double check, okay? Let's check each one by one. Is it reflexive? Yes, it is, because 0, 0, 1, 1, 2, 2 are here. Is it not anti-symmetric? The answer is it is not anti-symmetric right now because 0, 1 is here, 1, 0 is here as well, and 0 and 1 are not the same. So it is not anti-symmetric. Is it not transitive? The answer is it is not transitive because 0, 1 is here, 1, 2 is here, but 0, 2 is not here. So it is not transitive. Is it not comparable? It is not comparable because 0 and 2 are not related in any way. 0, 2 is not here, 2, 0 is not here either. Is it symmetric? It is symmetric. So this is the answer. I totally confused myself earlier. This is the answer. So are we good? Do you have an example where it is impossible? Not in this particular test. In this particular test, I made everything possible, but it is possible to make something impossible. I know how that sounds, but that's exactly what I meant. Okay, it is possible to list to have a list of properties where it is not possible. I can give you one that is very clear. Okay, that's very easy. I can ask you something where it is not reflexive, but it is comparable. That is automatically a problem because in order for something to be comparable, each element has to relate to itself, but in order for it to be not reflexive, we cannot have each element to be relating to itself, and therefore we have a contradiction because one side says we must have these things, and then the other side says we must not have all of these things. At least one of them has to be missing. So that's why we have a conflict in this case. Okay? So does that kind of answer the question of having an example of we cannot make everything right according to what the question is asking? Okay, excellent. All right, so we have one more. Nope, that's it. Okay, so we got 5 questions related to relations in the previous exam, which is no guarantee that you will have exactly the same format. And then we have question number 6 all the way to question 9. Those are all the CNF ones. Okay, so that means we're going to have to do a bunch of conversion to CNF, and then use that to answer the question. All right, so I'm not sure how much time we got now. Yeah, we got about 10, 12 minutes. Won't be able to finish all 4, but we'll be able to do at least 1 or 2. Okay, so we're going to use this as an example first. Okay, there we go. All right, so the first thing is we want to convert psi into its own CNF. Okay, so we want psi to be a CNF. All right, so let's check out how to do that. Okay, so we have a negation of not P, not P, not Q, and then the implication to R not Q. All right, so now we do the conversion. The first thing I usually do is to get rid of the implication, and that is just Markdown doing its thing. So I am going to put everything in code, into a pre-formatted code block here. So when we get rid of the implication, we have to negate the left-hand side, which means we have double negation, and then not P, not Q, and then we have a OR. Now we can use a plus here, to mean OR, and then the other side is not negated, so it stays as itself. And then we do a simplification, double negation goes away, so now we have not P, not Q, or Q not R not Q, which is exactly the opposite of what we want. This is DNF, or disjunctive normal form. We want exactly the opposite of this. So there are a few ways to do this. The quickest way is to FOIL. Okay, is to basically use a FOIL, and basically we end up with not P or R as one term, and not P or not Q as one term, and then we have not P, not Q or R as one term, and then we have not Q or not Q as the other term. Does everybody see how I just did a FOIL on this one? Okay, very good. And since the question is only asking you to make a CNF, technically speaking, this is a CNF already. However, if you want to do the resolution step, it might be helpful to simplify a little bit. Now, since you will be using Google Doc to do this, you can definitely do something along this line and just change the one term that you want to simplify and just make it not Q instead of not Q or not Q. Alright, so we got this one done, and the next thing we want to do is to turn the negation of the theorem into a CNF. So this is the theorem. Proposed theorem is phi, and we want to negate that. Okay, so once again, you'll start with a code block here, and then inside the code block. Now this is only when I'm using Joplin. When you are not using Joplin, you can probably just kind of copy and paste without using the triple backticks. Okay, so there we go. And Joplin doesn't understand that this is now within the code block because I have another block here. Oh, probably need a. Oh, right, because this is the close of the other one. I need another block here. There we go. Okay. So, but we have to negate it, okay? Because the theorem to be proven needs to be negated first before we convert it into a CNF. Alright, so let's take a look at this. Once again, get rid of the implication first. So the negation on the outside stays here. And then we have a not something or not P. And that something is just whatever was on the left hand side of the implication. So now we got this. Oh, yeah, it would be. Yeah, if you want to use a dot to denote logical AND, that's fine with me. Or if you want to use asterisk, that's fine with me too. But my shorthand is just not to have any symbol, because when we use xy in a normal expression, it means x times y. So that's just me being lazy, super lazy. All right. So at this point, we can use De Morgan's law, because De Morgan's law is going to spread this negation into the inside of this disjunction, and in the process turning all of the components into the negation of themselves, and then changing the operator or into an AND. Okay, so we're going to do that. Okay, so the outer negation is still here, and then we have not P and not Q and not R, and then we have a or not P over here. So in this case, I am maintaining the usual priority of operators. When you have an AND or multiplication, it is done before the disjunction. For those of you who say, but I don't want to deal with that, well, then we just put in extra parentheses. All right, so now what do? We simplify. Okay, so before we do anything else, we're going to simplify. So the double negation goes away, double negation goes away, and now we can, let's see, we can just apply De Morgan's law one time, and then we are all done. Okay, so when we apply De Morgan's law, we have the negation of P not QR, and then we turn that this or into an AND. And then we have not P on this side. There we go. And I'm going to use extra parentheses to make sure that it is clear what we are doing. So we are almost done, because somebody is going to say, but Jack, this is not a disjunction. Well, we're one step away of turning that into a disjunction, because we can apply De Morgan's law again. So once we apply De Morgan's law, we spread the negation to each component, and then turn the operator AND into the operator OR. And then the other one, we can just simplify to P, like so. And then one more step, just for simplification, we have not P or Q or not R on one side of the AND, and then P on the other side. All right, so I'm going back to the text channel here. Yes, Jonathan, it's okay to use a dot, and then Armand, it is okay to use a multiplication symbol if that is what you want to use, to make it clear to you. Okay, all right, cool. So now we have both in CNF. We have psi in CNF, and then we have not phi in CNF as well. So now we make the what I call this super CNF, which is the concatenation of the two. Now, if we are doing this on paper, this is going to take quite a bit of work. But since we are not doing this on paper, it makes it a little bit faster, because we can copy and paste. So here's copy and paste. All right, so this is the super CNF, and now we want to perform resolution. All right, so looking at this just intuitively, do you think we can get to a contradiction? Maybe. Well, I can see how the Q and the not Q can cancel out. So we can have not P or not R left here, and then the P can cancel out this not P, so we have not R here. There's a single R not negated here, and this P can cancel this one out, so I think we can resolve this. Okay, this definitely can be resolved. Yep. Okay, so let me go ahead and resolve this, and I'm going to indicate what I'm using for the resolution. Ooh, that is interesting, because the syntax highlighting, or the on this side, it's marking some of the variables as red. I don't know why. Okay, but I'm going to use a way to indicate what I am doing to do the resolution. So we can, okay, let's start with, let me see which way is the quickest. Because the P can be used to resolve with not P or R, it can also be used to resolve with not P or not Q. And then when we have R, we can, okay, there we go. So we're gonna resolve with this one, with this one over here. And once we do that resolution, okay, we'll copy and paste down here. So once we perform this resolution, we end up with a new term, which is just R all by itself. And then we can have, this may not be the quickest way, but it's certainly one way. So we'll take this not P and have it resolve with this P over here. So once we have that resolution, then we end up with a new term, and that new term is Q or not R. And then we want to get rid of this Q, and that's easy because we have this not Q over here. Once again, this is not necessarily the quickest way to do it. And Jonathan is, wait, what are you doing, Jonathan? Okay, we have this Q to resolve with this okay, I misspoke. We have this not Q here to resolve with this Q over here. So the end result of this resolution is now we are adding a new term, which is just not R. Now we are pretty much done because now we have this R, oops, to resolve with this not R over here. And now we have our false. Okay, so we have false all the way here. And that concludes all the steps of resolution, because once we have one false within the conjunction, then the entire conjunction is going to be false. But this is not the answer. This is not the entire answer. The entire answer has to say since psi and the negation of phi in CNF resolves to false, phi is a theorem of psi. There we go. All right, so we are running out of time. The other three questions are basically the same thing. Okay, you are given a psi, you have to convert psi itself into a CNF first, and then you're given a phi, but you have to negate phi first before you turn the negation of phi into a CNF. When you have two CNFs, you make a concatenation to make one larger CNF, and then you perform resolutions, okay, step by step, until you either come to a dead end and say, this cannot resolve any further and we cannot get to false, in which case, phi is not a theorem of psi. Or, like in this case, we do end up with a false, and as a result, this is by the principle of proof by contradiction, we can now prove that phi is indeed a theorem of psi. All right, so are we doing okay? At least, in principle. I mean, I couldn't finish all the questions because I spent too much time explaining implication. But that's important, okay? Implication is a very, very important concept. So is the universal quantifier. So you got to make sure that you understand those concepts really, really well in order to answer the first 5 type of questions. And then with these questions, you have to be good at Boolean algebra because you have to convert the whole thing into a CNF first. But that's basically just applying distribution and De Morgan's law, over and over again. And if possible, do some simplification so that you don't end up with a monster expression. But other than that, I mean, it's really just a matter of practice. I can give you the solutions, the answers to the other 3 questions. It's not a problem. I can give you all the answers so that you know the correct answer to the other 3 questions. All right, you're welcome. All right, so I'm going to have to end the lecture now. I have a meeting to go to at 6 o'clock, but I will still be able to have my office hour through text. So it's okay for you guys to ask me questions through the text channel of Discord. I simply cannot be having a video or voice chat at the same time. All right, you're welcome. And today is Wednesday, so that means let's see. Right. So next Wednesday is our exam 2. So when you're studying over the weekend, and you encounter some concept, issues, you might want to bring those questions on Monday, because Monday is the last lecture that for us to clarify the concepts before our exam on next Wednesday. So I just want to make it super clear that the exam is next Wednesday, which is about a week from now, minus 1 hour and a half. Yes, propositional logic and relations. That's the scope of the exam. I believe I said that on Monday. Yep. Oh, by the way, you can also watch the YouTube video during the exam too. Not really recommended, but you can. Alrighty. Okay, so you guys take care. I'm gonna stop the streaming and also the screen sharing so that I can get to the other meeting. But I'll keep an eye on the text channel, so if you do have questions, I'll be here to answer those questions. I'm gonna multitask.